Let's take a look at oxidation number. This is Dr. B, and the oxidation number is not the same as charge, although they do overlap quite a bit. It is the charge the atom would have if it were ionic. So if it is ionic, the oxidation number and the charge are interchangeable. But for lots of substances, particularly if they're partially organic in nature, have covalent bonds, this is a very handy thing to do. Think of it perhaps as a way to keep your math straight when you're trying to see what's going on in a chemical reaction where not everything has a clear charge. Does it reflect the absolute reality? I kind of doubt it. You get some funky numbers in here, but it's a good way to do the bookkeeping. We've got a bunch of rules. If it's just an isolated element, that means the atom, like sodium atoms, beryllium atoms, potassium atoms, they have a charge of 0. Now, these don't, potassium, for example, does not want to have a charge of 0. It's a very unstable atom, but you can buy potassium metal, and it has no charge. It has that one valence electron. It has not lost it yet. So circle the ones that have an oxidation number of 0. I guess it would be the noble gases. They're not charged. Chlorine doesn't have a charge. Hydrogen doesn't have a charge, right? Nitrogen does not have a charge. All the other ones do have at least a formal charge on them. Now, monatomic ions are pretty easy because the oxidation number is equal to just what it is, which is Li plus, I'm thinking plus 1, Fe 3 plus 3, oxygen dianion minus 2. See how easy that is? The oxides have a charge of minus 2. Watch out for peroxides, however, the O2 minus. Since there's two O's with a 2 minus charge, the oxidation number for each O must be minus 1 to total up to minus 2. So let's try these three forms of hydrogen. Atomic form is 0. I should say, I suppose, molecular form. If it's the hydrogen cation, that's plus 1, but sodium hydride, that's the hydride anion, is minus 1, and hydrogen can do that because it wants to gain 1 electron occasionally to become isoelectronic with helium. The group 1 and 2 ions, as well as fluoride, are pretty reliable because they'd be 1, 2, and minus 1 always. So that's good to keep in your mind. But for all the others, do the ones you know, and the missing one you can do by the math. Sound a little weird? Try these examples. Calcium. Well, I'm thinking it's just an atom. 0. Calcium fluoride. Each fluoride is definitely minus 1, and calcium's plus 2. No surprise. I'm using my periodic table and looking at the charge on the atoms, well, ions in this case, from their valence electrons. Calcium oxide, that's just plus 2 and minus 2. No funny business. Calcium hydride. Well, hydrides aren't that common, but each H must be minus 1 to offset the plus 2. Notice it always goes plus to minus, right? Sulfur dioxide. Each oxide does not change. This is minus 4 totaled up on the negative side. Sulfur must be plus 4. Similarly, we've got minus 4 from 2 oxides and another one. Well, it means it'll be minus 1 overall, so let's only go plus 3 here, since plus 3 minus 2 totaled up, because you have 2 of them, means plus 3 and minus 4 total. That means you have a minus 1 charge overall. Now we want to make these things so it's minus 2 overall, and we have a whopping minus 8 here. So if I make the sulfur plus 6, then plus 6 minus 8 equals minus 2. But don't forget that each oxygen is only minus 2. There happen to be 4 of them. Okay, 2 times something plus 7 of these, where minus 14 will still be 2 minus, so I think plus 6 works, right? 6 times 2 is plus 12, but minus 14, we are 2 minus, so plus 6 in each being minus 2 for the oxides. Plus 1 for sulfuric acid, right? Each hydrogen is plus 1. The oxygen is minus 2, so it's minus 8, minus 6. If sulfur is plus 6, that works out perfectly. Convince yourself that it's uncharged. Even if you have 8 of these, they all have to be 0 because those are just atoms. Carbon dioxide, let's try that. Oxide's minus 4, so carbon formally would be in the plus 4 state. Nitrate shouldn't it have a minus charge? Let's see if they did. Well, if it's just nitrogen trioxide, that's what that is, not the nitrate ion. I would definitely look for the negative charge, but if you don't see it, each of these is -2, and that's +6, and it works. Sulfuric acid, we did it right here, +1, +6, and -2. Iron oxide, and this is iron, what is that? Let's see, iron 3 oxide. So each of these is -6, is -2, totaling up -6. Each of those must be +3. For acetate, oh, lots of them here. We need to be -1 overall, so convince yourself that if this is 0, and that's +1 as they must be, that's 3, right? +3. 2 of these at -2 each makes -4. +3 -4, it's -1 already, so each carbon actually is in an oxidation state of 0. And it doesn't have to be whole numbers. Here we have iron oxide, but look at the charges. -8 on this side, and 3 of those should offset it, but a whole number won't do it, so you have to have a formal charge of 8/3 on iron. Yes, that is the correct answer. That's a look at oxidation number.